Yeah. So let's begin. Lecture 11. So we stopped talking about the ISM last time and started talking about galaxies, but there is an important topic in the ISM which I forgot to introduce. So I'm going back for a few slides for a discussion about the ISM. So the ISM can be in an ionized state. And this ionization can occur through various physical processes. The most common and easily understood process is photoionization from UV radiation that is coming from the stars. So naturally, any ISM that's there in the galaxy will receive a reasonable flux of UV radiation from stars, and that will lead to its ionization. Then the stars are also responsible for generating large numbers of cosmic rays. And some of those cosmic rays will be energetic enough to ionize the ISM, gas in the ISM. And if there is a lot of hot gas already, if the ISM is at high temperature, then you can also have collisional ionization in hot gas. And the balance between ionization and recombination determines the ionization state of the gas. And this is described by an equation that was first written down by Meghnad Saha, and that's called as the Saha equation. The key thing to remember is that the Saha equation works only under local thermodynamic equilibrium condition. It describes the ionization equilibrium for a gas. Okay? So what is this equation? This is the Saha equation. So Ni plus 1 Ni are the number densities of atoms in the ith and I plus 1 ionization states. Ne is the electron number density of the gas. And these two are statistical weights of the I and I plus 1 states. So these are usually determined experimentally. And then there are a bunch of fundamental constants, and then you have the temperature of the gas raised to the power 3 by 2, and then you have e raised to minus xi by kT. So what is this xi? It is the ionization energy to go from the ith state to the I plus 1 state. So obviously this will depend on what is the ionization you're doing and which element you have. Are you trying to ionize carbon, or are you trying to ionize helium or oxygen or whatever, right? And these constants will also be a function of both the value of I and the element that you're trying to ionize. So what are the things you can notice in this equation? So for example, if temperature increases, what happens? Gas will get more ionized or less ionized? More ionized. So this ratio will increase if T increases. What happens if electron density increases? Less ionization, because the way the ionization operates, the probability of it getting ionized will decrease if you have a denser plasma. And of course, these constants are to be determined experimentally, and these are basically quantum mechanical properties of the gas. And so this is the Saha ionization equation. I'll come to that in a minute. Okay, so ionization increases with temperature. It decreases with increasing the electron density. Different elements ionize at different temperatures due to varying ionization energies. Okay, So if you take this Saha ionization equation and you plug in the parameters for the Earth's atmosphere, okay, the number, density, temperature, etc., and then you calculate what will be the ionization fraction. Temperature is of course about 300 Kelvin. What do you think it will be? Will it be high or low? Take oxygen. Is oxygen ionized in our atmosphere? Is nitrogen ionized? Right? So the ionization fraction is virtually zero. Okay? Very, very small. Huh? Zero for all practical purposes. Yet the Earth has an ionosphere. How is that possible? Yes, there's low density gas. Anything else? But is that enough? Correct, correct. So there is there's an external flux, okay, of energy that's coming from the sun, which is causing the ionization. So if the sun switches off, the Earth's atmosphere will not be ionized. Okay? So that's the reason. So this is now an example. This is not really an example of local thermodynamic equilibrium, because the ionosphere is in local thermodynamic equilibrium, because it receives a certain amount of radiation and it radiates it out, right? And because of that, it maintains its temperature. But there are conditions, I'll give you conditions where local thermodynamic equilibrium is violated. And in that case, that thing is not true. Different elements ionize at different temperatures due to varying ionization energies. So now you can, with this Saha ionization equation, you can calculate by plugging in the temperature, densities, etc. Where is at what fraction on the surface of the sun, what fraction of the hydrogen and helium is ionized. You can calculate that. Okay? You would expect inside the sun, obviously, everything will be ionized. But as you go further and further and further away from the sun, the temperature keeps on dropping, and eventually you may not get a very high ionization fraction. It will keep dropping, except when you hit the solar corona, where the ionization fraction is high because it's ionized. It's a condition of extremely low density. So and there is no local thermodynamic equilibrium, those conditions. Okay. So we'll come back to non-equilibrium states, but when you talk about the ISM, you talk about equilibrium in at least 3 different ways. You talk of thermal equilibrium. Okay, there is a balance between the heating and cooling processes. In such situations, the temperature of the ISM will remain stable. It will not change. There can also be pressure equilibrium, balance of thermal pressure with other pressure sources. Okay, thermal pressure is there, magnetic pressure is there, cosmic ray pressure is there, turbulence related pressure is there, and that usually is constant. Why do we say it's constant? It's constant in the state of equilibrium, because all of these pressures together are going to be balanced by what? Gravity, self-gravity, which is trying to pull everything inwards, and there will be these pressures which keep the material from falling in. And there can also be ionization equilibrium, because if all of these are constant, so if the pressure is constant, the volume can remain constant, the density will remain constant. If there is thermal equilibrium, then heating and cooling is balanced, so temperature is constant. So if density and temperature are constant for a given plasma, the Saha equation will tell you that there will be a balance between ionization and reionization and recombination rates. So the fraction of ionization fraction will also remain relatively unchanged. Okay. So there are various heating and cooling processes that operate in the ISM. Heating can be this photoelectric heating from the dust. Cosmic ray heating is possible. X-ray heating is possible. Shock heating is possible. Okay. So what is shock heating? Where do you expect to see these kind of shocks? Supernova. So that's the most common location where you will see very, very strong shocks, and they can compress material to very, very high densities, and they can heat up the material. X-rays, if there's a lot of X-ray flux, maybe due to an AGN, for example, that can heat up the interstellar medium. Cosmic rays will also transfer energy, and heating from dust will also happen. Line emission. So cooling processes in the ISM also are numerous. There is first of all line emission. Okay, C2 line, O1 line, and so on. Okay, so this particular line, which occurs in the infrared, is a very, very efficient cooling line. So if you see that line, that means that that gas is likely to cool very rapidly. It's a very efficient way of cooling the gas, and you will eventually form molecular gas, and you will get star formation. So this is a tracer of star formation, carbon line. There's continuum emission from the dust. So you heat up the dust, that will emit not just lines, but it will emit the continuum. And there can be free radiation also, which can also operate in the ISM. And the ISM is not static because it can expand, right? So it can adiabatically expand, and you can have this kind of adiabatic cooling, which happens in the ISM. Now, the exact temperature of the ISM is determined by the balance of all the heating and cooling processes, right? Some of these are very non-equilibrium. For example, shock heating. Shock heating only occurs at a particular point in space at a particular time. It is not a continuous process. So it definitely is a non-local thermodynamic equilibrium kind of situation. So what are these non-equilibrium conditions? Okay. Many regions of the ISM are not in equilibrium. Dynamical processes like turbulence and shocks can drive the ISM out of equilibrium. And they are often associated with star-forming regions, supernova remnants, and galactic outflows. So these are the areas in which, if you want to use local thermodynamic equilibrium, then that is incorrect. So one should not, in a supernova shock or in a supernova remnant, one should not try to apply the Saha ionization equation. It just doesn't hold. Galactic outflows are mostly driven by active galaxies, the supermassive black holes at the centers of galaxies. Okay, so one announcement, I'll send out an email also. No class next Tuesday because I'm out of town. But we will do a makeup class on Wednesday, 18th September. I hope that's all right for everyone. So I'll send out an email, maybe early next week, or I'll send it out on Sunday or something. So at 10 a.m., the usual time. And one hopes that by next week, we will finish all the classes, right? Because this is class number 11. Lecture 12 is on Thursday. 13 and 14 I'll do next week and finish off. Okay, so now we've come out of that detour back into the ISM and come back to galaxies. So when galaxies form stars, they don't form all stars of the same mass. Okay, they form stars of different masses together. There'll be some massive stars, some less massive stars. Okay, and as expected, the distribution, if you plot a histogram of the masses of the stars that are formed, that will be a power law. It's called as this function is known as the initial mass function. So it is the mass distribution of stars in a star cluster when it is formed, right? All of them, for all practical purposes, are assumed to have formed at the same time, right? Because typically what happens is when a large giant molecular cloud forms, it fragments, and each fragment then collapses under the self-gravity. and form stars. So from one big giant molecular cloud, you can form many, many stars of different masses, right? So this function specifies the distribution in mass of a newly formed stellar population, frequently assumed to be a simple power law of this form. In general, this is assumed to extend from a lower mass to an upper cutoff, M2. Okay. This is just written in this format so that when you take the derivative, then it becomes m raised to minus x kind of. So you don't have to. So this is nothing. This x is the power law coefficient, which is important, and this is just a scaling relation, right? So this is what. So there are different initial mass functions. The most earliest one and still relatively widely used is the salpeter IMF, which says that the minimum mass M1 is 0.1 solar masses, M2 is 125 solar masses, and the power law index X there is 1.35. Okay. And then people said, no, this is very simplistic. Okay, a single power law is not good. Let's have multiple power laws over different mass ranges. So then Scalo came up with this IMF. Okay. The Miller and Scalo said, no, this is not right. This is a better IMF, and so on. So there are, I've shown you 3 IMFs, but there are at least half a dozen more different IMFs that are widely used in the literature. Huh? Yes, that is actually negative.
There are more high mass stars.
Yes, below, as per Scalo, at the lowest mass end, it already begins to fall off. Because remember, there is a truncation here. Below about 1/10 solar masses, you don't form stars, right? This was a question in your exam. You don't form stars because you don't have enough temperature at their center to fuse hydrogen. So they form brown dwarfs, right? Below these masses. But what Scalo said is, no, there shouldn't be an abrupt cutoff like that. Okay, let's turn it around and pull it down. And other people said, yeah, we'll pull it down, but not make it increase and so on. So anyway, so these, there are very, very detailed papers describing each of these IMFs. Okay, and they will tell you exactly what is the physical justification for the kind of slopes that they have arrived at for the power law. Okay, so this is a question you don't have to do now, but you can go back and see what is the relative number of K and A stars in a cluster that has just formed. So you need to know the typical mass of a K-type star and a typical mass of a A-type star. Which one will be more numerous? Huh? K-type. K-type will be more. Less massive stars are always more numerous than more massive stars. Okay, so now we come back to galaxy morphology, which we were discussing last time, ellipticals and spirals and so on. So in some cases where we have looked at galaxies at their very center, so this is a big spiral galaxy. And at its very center, however, you see a spiral structure. So it's like a spiral in a spiral, okay, almost a fractal-like appearance. Okay, so this tells you that these spiral arms may be quite fundamental in the sense that they're quite ubiquitous. They appear, and we will talk a little bit more about them. Then, when we looked at the Hubble tuning fork, there were 2 arms of the tuning fork. One contained unbarred galaxies without a bar, and the other is the barred galaxies. So barred galaxies are approximately half of all the disk galaxies, and Milky Way included. Milky Way is also a barred spiral galaxy. Shows this kind of type of galaxy shows central bar, which can contain up to 1/3 of the total light. Usually it's much less than 1/3, but in some extreme cases, the bar can contain 1/3 of the light. H0 galaxies also have bars. A bar can persist in the absence of gas. Right. So the bar, what is it made of? It's made of stars. It's a stellar bar. It may also contain gas, but it necessarily contains stars. Bar patterns are not static. They rotate with a pattern speed, but unlike spiral arms, they are not density variable. In the bar, stay in the bar. So what does this mean? This means there's something different between the bar stars and the spiral arm stars. So spiral arm stars are believed to be what is called as a density wave. So what's a density wave? Suppose you have traffic on a highway, and suppose there's some accident which has happened somewhere on the highway. What will happen to the cars there? The density of cars, it will increase because all the cars will slow down near the accident spot. And then once they go past it, they will again speed, right? So if you look at it from space, that little traffic jam will look to you as a high density region for cars, right? Similarly, that is what happening in spiral arms. So in spiral arms, there are stars which are moving through, right? Slowing down because of the increased density over there. And then, but continuing their travel. They are not completely halted by the gravity. They continue their travel and then they eventually get out, right? And of course, they don't necessarily speed up, but they continue with their speed. Okay. So unlike this, bars are stellar bars. So a star in a spiral arm today, 100 million years ago, 200 million years ago or later, will not necessarily be in the spiral arm. It will be outside. So the sun, this also explains why stars like the sun exist, right? The sun has passed through a spiral arm several times of the Milky Way. It is presently not in a spiral arm. It's in the region between two spiral arms. But it was born very likely in a spiral arm, because in the spiral arm, you have a lot of molecular gas, high density. All the open clusters are sitting in the spiral arms. All the young stars are in the spiral arms, etc. So stars get born in the spiral arm, but they eventually leave it. So the asymmetric gravitational forces of a disk allow gas to lose angular momentum, compressing the gas along the edge of the bar. The gas loses energy and moves closer to the center of the galaxy. So the bars are also responsible for transferring gas to the central regions of the galaxy. And in the central regions of the galaxy, you have prominently the bulge. So the bulge can grow. It can form new stars and it can grow in size and mass due to the fueling of gas from the outer regions to the inner regions through the gravitational potential of the bar. So this is a fantastic example of a barred spiral galaxy. So this is the bar. So this is the bar, right? And these are the two spiral arms that are coming out from the edge of the bar. And typically galaxies with a strong bar like this one will have only two spiral arms, which will start from the end of the bar. So the bar comes out from here and ends over here. Similarly here. Disks of galaxies are not necessarily stable. Okay, there can be lopsidedness, as you see in this image. Okay, they're not necessarily in the same plane all the time. The stars, there can be motions along the z direction, and that can produce these kind of lopsided features. The last type of galaxies, which actually don't find a place on the Hubble tuning fork diagram, are irregular galaxies. Irregular galaxies are often star forming, not always, but often star forming, very heavily star forming. Some of them can be very low metallicity objects. So this means that that galaxy is forming stars for the first time. Because if you have formed stars in the past, you would have polluted the interstellar medium. The metallicity will be high, and when new stars form, they will be having high metallicity. So the stars in this galaxy have very, very low metallicity, and they are therefore very interesting, because when did we last have this in the universe? The first stars, the population 3 stars, were exactly like this. They formed in small galaxies and they were very low in metallicity. So these are the nearby counterparts of very distant galaxies which form the first stars. And since they are nearby, we can study them in greater detail. Which one? This one, we don't usually call them population 3, but in some sense they are. So population 3 usually refers to the highest redshift, because these kind of objects are very rare. The very low metallicity galaxies amongst the irregulars are very rare. Right? And even these are not like truly zero metallicity. The true population 3 stars are essentially zero metallicity. Right? There's very, very tiny amounts of primordial lithium which is there, but nothing else. Okay. So in the nearest irregular to us are the two Magellanic clouds, the large Magellanic cloud and the small Magellanic cloud. These are in fact satellite galaxies of the Milky Way, and they are losing energy. They are sort of inspiraling towards the center towards the Milky Way, and they will in several billion years they will merge with them. This is, if you, with a telescope like the Hubble Space Telescope, you can actually resolve individual stars inside the LMC. And in this particular image, there are more than 20,000 stars, which can be seen in a very, very tiny portion of the galaxy. Now, what is the black portion? So this is the detector. This is a camera on the Hubble Space Telescope, which no longer exists, which is called the Wide Field Planetary Camera 2. So that has one detector like this, one detector like this, and a fourth detector, which is smaller in size, but has a better resolution. That's called the planetary camera. And this is called the wide field camera. So they're just 4 different sensors. And this black is because the telescope is not, the detector is not covering that area. Okay, so you will also encounter for galaxies nomenclature like this, which is called early and late time. Objects which are to the left of the Hubble tuning fork diagram, which means closer to ellipticals, those objects are collectively called early type. So ellipticals and S0s, we will call them early type galaxies. And spirals, we refer to them as late type. And within spirals also, an SA galaxy is called an early type spiral, and an SC galaxy is called as a late type spiral. Okay. However, this is not a statement of the evolutionary stage of the objects, purely historical origin. 100 years ago, Hubble and others thought that maybe there's a sequence like this. Ellipticals change into spirals over time, but truly not. There is no connection. If anything, spirals transform into ellipticals, but it's very hard for an elliptical to transform into spirals. So, if you look at distant galaxies, if you look at galaxies at redshift 1, redshift 1 is interesting because it is approximately halfway to the Big Bang. It is about 7 billion years in the past. And if you look at the morphology of galaxies, then you do see some disk-like objects. You see objects resembling ellipticals like this one, but you see many objects which don't look like anything we know, right? Hard to call it spiral, elliptical, or lenticular. or irregular. Maybe you can call it irregular, but it's not even truly an irregular. Now we know in hindsight, initially we thought that this was used to mistakenly claim that the Hubble sequence was not in place at redshift 1. It didn't exist. And it formed later on. In the last 7 billion years, all these spiral galaxies, etc., emerged. But now we know, and I'll show you when we talk about high redshift galaxies, I will show you images taken with the JWST of galaxies at redshift 2 and 3, which show a clear spiral arm, elliptical shape, or whatever, lenticular. We can't, the morphology that you're seeing here is not seen in the JWST images. And the reason for that is relatively simple. What is happening here is that at redshift 1, with the Hubble Space Telescope, if you're, let's say, observing at 6,000 angstroms, you are observing the rest frame 3,000 angstroms. So you're observing in the near UV. And in the near UV, we know that the morphology of galaxies changes. So only if you observe in the rest frame optical. Okay, so do you guys know this? So the definition of redshift is like this. Lambda observed is equal to 1 plus z times lambda emitted. That's the definition of redshift. So if a galaxy is at redshift 1 and it is emitting light at, let's say, 3,000 angstroms, you will see that light at 6,000 angstroms. So you are observing in the UV, the rest frame UV. So that's called rest frame. So this is called rest frame. This is refers to the observed frame, right? So in the observed frame, we are observing the galaxy as it would look in the UV. And that is leading to a very, very strong bias. With the JWST, now we are able to observe the rest frame optical. So with the JWST, for example, if it is emitting at 6,000 angstrom and it's at redshift, let's say 2. So this will be 3 times 6,000, which will be 18,000 angstroms or 1.8 microns, which the JWST can comfortably observe. HST can't, right? Therefore, you get a more complete picture. You get an apples to apples comparison with nearby galaxies. And we'll talk about that a bit later. Mergers. So galaxies can undergo mergers. And when they undergo mergers, their morphology can change. Okay? So this is a group of pair of galaxies which are merging. Okay? And these are called the tails. These are called tidal tails of the galaxy. Okay? What do you think those tails are composed of? Dust, gas, stars, what else? Which one of them? Stars. So they're composed of stars. And that is why you can see them even when the stellar density is quite low, you can see them out to great distances. So because during the collision, because of tidal forces, things can get completely thrown out. I mean, the stars which are in stable orbits can get completely scattered out of the galaxy, and they can form these very, very long tidal tails. Okay. So the Milky Way and the Andromeda galaxy are about, not about, they are in the future going to undergo a merger. This will lead to a transformation of their morphology. And generally one goes from disks to ellipticals. You can understand this in terms of entropy, right? The spiral galaxies have very regular orbits. Okay, they have a lower entropy than the elliptical galaxies, which are high entropy systems. So you go from low entropy to high entropy when the merger happens. And what does a merger product look like? So I'm going to show you a movie of Okay. So this is a movie. 1 second is 100 million years. The galaxy rotates once every 200 million years or so. This is our Milky Way galaxy. Things are really speeded up, of course. And nearby, this is the Andromeda galaxy. There is a third reasonably big galaxy called the Triangulum galaxy. This does not participate in the merger, but it obviously affects the gravitational potential of these objects. And Andromeda is a more massive galaxy than the Milky Way. And they're going to collide like this. Okay. So remember, stars are not collisional, so the stars will pass through. Okay. But again, they will feel each other's gravity. They'll come back. They'll come back. They'll come back, and eventually they'll merge. Okay. And it'll leave behind. So what is this merger product looking to you like? Elliptical galaxy, right? The two spiral galaxies have merged and formed eventually a elliptical galaxy when 7 billion years in the future. Okay, not right now. A long time in the future. So when the merger happens, there are two kinds of mergers. One is a major merger and the other is a minor merger. In minor mergers, the mass ratio of halos is large, typically in excess of 3:1. And major mergers where the two masses are similar. So why do we see halos here? What is actually happening is that the dark matter halos are merging. There is a dark matter halo of the Milky Way. There's a dark matter halo of Andromeda. They feel each other's gravity. They come together and they merge into a larger halo. The galaxies are carried with their respective halos and they also merge. So one uses the mass ratio of the halos. If it is greater than 3:1, then you have a minor merger. Otherwise, you have a major merger. So in the case of Milky Way Andromeda, that's a major merger because they are comparable in mass. Andromeda is somewhat larger. Which type of merger will be more common? Major merger or minor merger? Okay, take a big galaxy like the Milky Way. I should probably justify this because what is actually common is major merger of small galaxies. That is much more common than. But in today's universe, if you're sitting in a massive galaxy, the likelihood of merging with a minor galaxy is much higher because they're much more numerous, right? In the local group, again, as we shall see, there are only 3 big galaxies, right? And there are about 30 small galaxies. So the chances of a minor merger are much higher than a major merger. So you will also encounter jargon like dry merger and wet merger. Dry merger is a merger between gas-poor galaxies. And a wet merger is a merger between gas-rich galaxies. So Milky Way Andromeda merger, what type of merger is it? What do you think? Huh? Wet merger, because both are spiral galaxies, both are rich in gas, right? And this is going to be a wet major merger. What are the observable differences between these two types of mergers? What do you think will happen?
Dry merger should be reddish.
Yes, and wet mergers? Bluish. Because of? Yes, absolutely right. So in the case of a dry merger, there's no gas to form stars. So the things are just going to pass through and come back eventually and merge, right? The stars. But in the case of wet merger, the gas is collisional. The gas will collide. And when it collides, it will produce shocks and turbulence and everything. And that will lead to star formation because of the shock compression. And that a large amount of gas will get transformed. So in fact, when the Milky Way Andromeda merger happens, there's going to be a phase when a lot of star formation will happen. And that merging galaxy system will form stars at maybe 50 times, 100 times the current rate. And that period will last for a short time. All the gas will get exhausted and it will settle down as a elliptical galaxy. So in terms of their star formation properties, one can see direct observables between these two types. If you look at with sufficient sensitivity at even elliptical galaxies, you often see signatures of recent or past mergers. And so you see these what are called shells, right? So the main galaxy itself is only this much. If you don't make sensitive observations, you'll only see one elliptical galaxy and one spiral galaxy next to it, right? But if you make very sensitive, what these are called low surface brightness kind of observations, then you see evidences of merger. Because this is the only direct evidence. After the merger is complete, how do you know if a galaxy has undergone a merger in the past? You make these kind of observations, you see this. And many elliptical galaxies show this kind of structure, indicating that they have undergone mergers in the past. Okay. So an interesting effect happens when a galaxy passes through, let's say a dwarf galaxy is passing through the disk of the Milky Way, right? What happens is this galaxy is moving relatively fast, right? And because of its gravity, it begins to attract these other stars or star clusters towards it, right? And if it is traveling in this direction, because of this sort of delayed potential kind of effects, this leads to an accumulation of matter along the track that object has taken. So by the time, so for example, here these guys are feeling gravity from this galaxy and they're getting pulled in this direction. So they acquire a certain velocity. But by the time they come over here, this galaxy has moved on, right? And so this leads to a pileup of material behind the galaxy. And what will this lead to? How will this affect the speed of this galaxy? It will slow down. It will get slowed down because now there is excess material that has accumulated behind it, which is trying to gravitationally, of course, attract it and slow it down. So this galaxy will get slowed down and it will lose energy. And this process is known as dynamical friction. Okay, so why are the most massive galaxies in a cluster found near its center? So where do you think in a cluster, where will be the deepest potential? At the center, correct? And therefore, material will get attracted towards the center. And if you form a galaxy at the center, then that galaxy will undergo many mergers because many galaxies are getting pulled towards the center. Once they come close to the center, this galaxy will merge with them. And if it undergoes many minor mergers, then over time it will grow in size and mass. And therefore, you will eventually, if a cluster has formed a long time ago and has had enough time to swallow smaller galaxies, it will form its most massive galaxy will be at the center of the cluster. These kind of galaxies we saw already are labeled as CD galaxies, always found at the center of the cluster and almost always ellipticals because If it's a spiral, it can't maintain its entropy because galaxies are falling towards it from all sides. Yes. Center of mass. Center of mass. So you do a mass model that, of course, is not very simple because there's a lot of dark matter. You can't just take the galaxies that you're seeing in the cluster and the gas that you're seeing in the cluster and find the center of mass. Okay, you have to know what is the distribution of dark matter in that cluster. And for that, a technique known as weak lensing or strong lensing is used. Gravitational lensing is used to figure out. Yeah. Why do supermassive black holes also merge during a galaxy merger? Okay. They have to merge because, again, these kind of dynamical friction type effects will play a role. And when the galaxies merge, the black holes will begin circling each other. Okay? And due to dynamical friction, they will lose energy and they will come closer and closer and closer to each other and eventually merge. What will happen to with the Magellanic? Can you detect these kind of mergers using LIGO? No, because its frequency is all wrong. LIGO is sensitive over a range of frequencies. This is going to be very low frequency radiation. If no, they don't collide necessarily because it's not as if they're targeting each other and like two bullets hitting each other. It's not like that. So they will merge eventually. So what will happen is they will come closer to each other when the galaxies finish merging. These two black holes will be there somewhere inside, and they, due to each other's gravity, they will start an in-spiral. And they will come closer and closer. They will not collide directly in a straight line like this. They will go into a spiral, and they will eventually merge. So the frequency of this is very, very low. The gravitational waves are of very low frequency. So you, which means very, very long wavelengths, right? Which means you need different techniques. Okay, one is to use space-based interferometers, but even they won't be enough. These wavelengths could be light years or many tens of light years. And therefore, you use what is called as a pulsar timing array. There are people in NCRA working on these things to actually measure the stochastic gravitational waves from these kind of supermassive black hole mergers. What will happen with the Magellanic clouds in the distant future? That I've already told you. These are going to merge with the Milky Way. Why can't compact groups be very old? So what is meant by compact groups? Groups of galaxies which are very small in size. They would have merged by now, right? So they cannot be too old, because if you pack in so many galaxies in such a small volume, they will eventually merge. So in galaxies, like dynamical friction, dynamical time scale is also important. It's a typical time taken to cross a massive structure. It's indicative of the time to reach equilibrium in the system. For a Milky Way type galaxy, for its size and mass, it's about 10 raised to 8 years. For a cluster, it's 10 raised to 9 years. Most clusters have not yet reached equilibrium because they have not formed that recently. What is the dynamical time scale for the Earth? How will you calculate that? Is the time required to cross the structure. So if you dig a tunnel through the Earth and you drop a rock, how long does it take to perform an oscillation? Okay. Does anyone know this? So it takes about 42 minutes. That's the period. It will be like a SHM if you assume uniform density. So it'll take, so that's the dynamical time scale here. For it's only 40 minutes For Milky Way, it's 2 into 10 raised to 8. Of course, it's very big, very massive. Okay, so now one more concept, which is quite important, and it is everywhere in astrophysics, everywhere, literally. If you go and look at the night sky, most of the stars look white or blue with a few red ones, which are all red giants, right? But the IMF tells us that most stars should be red-looking M dwarfs or G and K type dwarfs, right? Why are these common stars extremely uncommon in the night sky? They're very faint. So then what happens? By naked eye, right? So if they're very faint, what will happen? So if it's at the same distance as a bright star, what will happen? You will not detect the low luminosity star, right? You will only detect the high luminosity star. Or in other words, if there is a high luminosity star, you will detect it to higher distances, right? And when you go, so suppose you take a telescope now, which can detect stars which are, let's say, 10,000 times fainter or 1,000 times fainter. What will you see there? Will you see a lot of M, G, and K stars? Huh? No? No. The actual answer is yes. You will see. If you take a fairly sensitive telescope, you will see lots of G and M and K types. Huh? No, you run out of bright stars. That's the problem. See, remember one thing. Bright stars, yes, they can be seen further away. But B, they're not very numerous. And B, they're so bright that you'll be able to see them to the edge of the galaxy, to the other side of the galaxy. And so once you see all the bright stars, I mean, let's not say bright, all the luminous stars, high luminosity stars, you'll run out of high luminosity stars. After that, as you go deeper and deeper, you will find low luminosity stars. So another peculiar effect is occurring here, is that if you calculate the average distance to the stars you are seeing with naked eye, right? You calculate some number X. Then you take a telescope and you measure many more stars, right? And you calculate the average distance to those stars. What will happen? Intuitively, you will expect that, okay, I'm seeing fainter stars. So therefore, the average distance should increase, right? But actually, the average distance decreases. The average distance decreases. The average distance to the 10 brightest stars in the sky compared to the average distance of the 10,000 brightest stars in the sky. 10,000 brightest stars are closer to us than the 10 brightest stars on average. Okay, so this kind of bias is extremely common in astronomy because of what we usually do, which is we do what are called flux limited surveys. Okay, we say that I am sensitive to a certain flux level. I don't want to go deeper than that. So because of this, you will find luminous objects at high distances and all luminosities at low distances. Luminous objects are always rare. Okay, so you will find them you need a higher cosmic volume to sample them, which you can because you can see them to higher distances. And the faint objects will be at closer distances. This kind of bias is referred to as the Malmquist bias. Okay, and you should be aware of this. You will encounter this kind of bias in every situation, and you should be able to correct for it in some fashion, right? Otherwise, you'll be completely misled. Because if you go look at galaxies at high redshift, you'll find they're all luminous, right? And at low redshift, there are low luminosity. Then what will you say? Oh, there are no low luminosity galaxies at high redshift. That's not correct. What is correct is I am only with my detection methodology, I'm only able to detect high luminosity galaxies at high redshift. I cannot detect low luminosity. I'm not, they're too faint for me to detect. So in Binney and Merrifield's book, which is one of the books that is listed on our course website, if you go through these 3-4 pages of text, that is very, very informative about what exactly this Marquis bias is and where it operates and how one can correct for it. Okay. So now we begin to talk about the large scale structure as traced by galaxies. So we have looked at galaxies and their components, bulge, disk, star forming regions, spiral arms, etc. The physical scale of these is a few tens of parsecs. So the diameter of our Milky Way is about 30 kiloparsec or 100,000 light years, 1 lakh light years. This is a big galaxy. Most galaxies, very few galaxies are bigger than the Milky Way. So this is also an interesting idea that the Earth, we said, is not in a special place. We extended that idea within our to our solar system, that we said the sun is not a special star, which is also correct. The sun is not in a special place in our galaxy. That is also correct. Okay. But if you said the Milky Way is not special in any way, that is not correct. Because the Milky Way, in terms of its mass, if you rank galaxies by mass, the Milky Way is above 95th or 96th percentile. So there are only 3-4% of galaxies in the universe, in the nearby universe, that are more massive than the Milky Way. The Milky Way definitely is special. It's a very, very large spiral galaxy. It's a very, very old galaxy, etc. It is not the ordinary galaxy. So some people have said that this is where this principle breaks down. Maybe life can only evolve in such large galaxies. So that, of course, is an open question. Yeah. So now we look at the large scale structure of baryons in the universe on megaparsec scales. So just as stars are individual building blocks of galaxies, galaxies are building blocks of the cosmic web of large scale structure. Remember, however, that galaxies are biased tracers of the underlying dark matter distribution. The mass to light ratio, where mass is the total mass, including the dark matter, and light, of course, is coming only from the baryons. This ratio is not constant in the universe. It changes, not by a huge amount, but maybe an order of magnitude. It changes. So in order to use these galaxies as tracers of the underlying distribution, we have to conduct galaxy redshift surveys. Yeah? Because density fluctuations evolve into structures we observe, like galaxies, clusters, etc. On scales much larger than galaxies, we refer to the LSS, large scale structure. And that large scale structure is composed of groups of galaxies, clusters of galaxies, filaments of galaxies, walls of galaxies, voids, regions where there are no galaxies, superclusters. All of these are elements of the large scale structure. To map and quantify the LSS and to compare with theoretical predictions of cosmological models, we need redshift surveys. So basically, we need to map the 3-dimensional distribution of galaxies in the universe. Today, we have redshifts measured for greater than 2 million galaxies. And this number will change very rapidly because there's a survey known as the DAISY survey, which has just gotten going. They're going to have a data release next year, where this number could jump from 2 million to 10 million. While the existence of clusters was recognized earlier on, it took a while to recognize that galaxies are not distributed in space uniformly randomly, but in coherent structures. So before you do a spectroscopic survey, you have to do an imaging survey. So in 1970, there was this survey where they had 1 million galaxies. Then 2 million galaxies by 1990. 1995, 50 million galaxies. Then the SDSS came in 2005. By 2005, they had discovered 200 million galaxies. And now, next year, this is wrong actually. There's also a typo here. Next year, a survey called the LSST survey will start, which will, in an imaging survey, discover 20,000 million galaxies, which means 20 billion galaxies. Remember, in the observable universe, there are about 100 billion. So 20% of them will get actually seen by this survey. And then people, once you do imaging, then you say, okay, let's go do spectroscopy of the more interesting objects. So similarly, there has been an exponential growth in spectroscopic surveys. So the CFA survey in 1985. So 1995, when I was here in the graduate school like you, only 20,000 galaxies had their spectroscopic redshift measured. Okay? So those numbers remained stagnant. And then you had something known as the 2D field in 2003. They did 250. By 2005, SDSS had done 800,000 galaxy redshifts. And by 2017, SDSS had done 2.5 million. Okay, so all these redshift surveys, particularly the spectroscopic redshift surveys, allow us to map the three-dimensional distribution of the large-scale structure in the universe. And next time we'll look more closely at the large-scale structure and how that can be quantified, how can that be measured in order to test the predictions of these cosmological models. So we are gradually now going to the larger scales. Eventually we'll hit cosmology within the next few lectures. Talk about that. Yeah. So we can stop now and we'll meet again on